to Los Angeles Data Platform user group. Today we have a session by Rob Farley. The session is problem operators. Rob. Sponsors of this event is Data Driven Technologies, is the nonprofit that funds the user group and it also funds the SQL site in Los Angeles. I'm your host. My name is Steve, and Rob, take it away.
Cool, thank you. I'm going to stop sharing my camera for a minute, and I'm going to share my camera instead through screen share. Terrific. Cool. Hopefully that's working. Hopefully you can see me. It's probably easier than doing the whole spotlight thing and so on. And anyway, it's all good. So, yeah, my name is Rob Farley. As you can see, and my contact details are there. My email address, where I blog, and that's my Twitter handle. Feel free to reach me on. I saw the list of people that are on the call, and I recognize some of the names, which is nice. But I apologize already that I can't see the Teams window. So if you need to ask questions or whatever, please just unmute and jump in, interrupt me. That'll be fine. And please do, because at the end of the day, if you have a question, it means that I've explained something badly. It's a reflection on me, not on you. So please jump in. Anyway, so today's topic is on problem operators. The idea being that when you have a query and you look at the plan, and you'll see that you've got like something like maybe you've got a select. I'll draw over here. You've got your select operator, and you've got various things that are feeding it, and so on. And you might have some joins and things like that that are consuming two. That are pulling data from two other operators. When you have a query plan, what are the things that you notice in there that might deserve some attention? Right? I say problem operators, they're not necessarily actual problems. More than likely, they're things that I just want to be across what's going on with them. Maybe it's a clue that I can address some potential issue. It's just something that's grabbing my attention, making me want to fix something up. And of course, always, the query optimizer has put those operators in there because it thinks that it's the best idea. Okay, it's not doing it just to be annoying. The idea is not for you to just go, well, I'll force it to not use that. No, it's there because it thinks that the best way of running your query is to do it this particular way. And even if that you don't like that thing there, it's put it there because it thinks it's the best option. So maybe you need to change your query. Maybe you need to change some of the indexes and so on. Redesign some tables, whatever it is that you need to do to be able to change the environment so that the query optimizer can make a better choice and hopefully address some of the things that I'm going to point out today. Okay, let me get rid of that. So I'm going to go through a handful of operators. Some of them, the whole operator is the problem. Some of them, it's only in certain scenarios. Sometimes it's only particular properties that I want to be across. But the idea is for you to be able to start jumping into plans and instead of just being able to go, oh, look, I know that I want to see seeks instead of scans, for example. I want you to have a deeper understanding of what you should be keeping your eye out for, of what kinds of things might warrant some attention, how to address some of those things, and really, I suppose, just become more fluent in execution plans. I was just telling someone before, actually, someone who said they were going to join this session, except for the fact that they're in the East Coast and they're trying to go to bed already. Those people on the East Coast, I don't know. We have an East Coast here too. It's a half-hour time zone difference from here. It's not like 3 hours like what you've got. It's 3 hours time difference from Perth to the East Coast of Australia. But I'm in the middle. I'm half an hour to all day driving, but half an hour time difference. I was just saying about the fluency, the concept of being fluent in execution plans, and how when I teach SQL to absolute beginners, people who have never written a query before, they don't even really understand the concept of tables, let alone anything else. I straight away introduce them to execution plans, and I encourage you to be thinking about execution plans at the moment you start thinking of a query. Think about what the plan is, how it's going to run, because it's easy to write a query that's logically correct. It's much more of an art form to be able to create a query that's logically correct, that performs a way that you're happy with. And if you're writing a query in isolation and not thinking about the indexes that query is going to be helped by and so on, then really you're doing a disservice to your DBAs. So always be thinking about what the impact of your whole environment is on the way that queries are running. Become familiar with that. Be, just generally fluent in execution plans. But today we'll be looking at some of the things that I think are more significant than some other things. The first one that I want to be mentioning today is the index-full operator. Okay. I'm not going to show you any proper demos. I'm going to be drawing diagrams on my screen like this. Okay. The index-full operator. The concept of, I think probably need to sit back here a bit to make sure that the white balance makes sure that wall is sufficiently good for writing on, so that I can put my words in the air. We're all good though, I think. What we see with an index-full, typically we'll see an index-full operator being, somewhere, pulling data in from somewhere else, and the thing that's consuming this, the thing that's calling the index-full, that's saying get me a row, is typically going to be a nested loop operator, and with some other data coming in here. So the nested loop is saying running here, saying give me data from that top, from whatever operator is there, and then for everything that comes in, go and pull data from this other branch, right? And when the thing that's there is an index full, what it means is that the query optimizer thinks that the quickest way to run this query is to create a temporary index of the data that it's pulling in from here, right? It's basically saying, if I could persuade you to be able to go back and if I could persuade you to be able to create an index before you run this query, then I would do that, but you haven't. The ideal index for me to run here is not available. And I think it's going to be cheaper to create that index every time I run this query for you. I'm going to create a temporary index of that data before I, so that this query can run as if that index is there. And it's just a little time consuming, right? And the more data that comes in here and so on, and it's creating something. And I'll run a query and it will take a while, and I'll be like, hang on, what's going on? And I'll show the live query statistics, where you've got a plan that's with all the dotted animated lines saying, oh yeah, we're pulling data from here, it's moving through here, it's moving through here, and I'll see that data is pouring along here, being pulled in by the index full operator. And this can't give out any results until it's been populated typically. And the whole time, I'm just going, I should create that index. The index that is that the system thinks it wants. I should just create that index. And almost always, that's how to address it. Now, it can be more tricky than that, because over this operator here might actually be a someone's not muted. I can hear a lot of noise, unless that's me. But anyway, the data that the index spool is pulling in might actually be the result of joining other things and so on. It might not be particularly easy to create that index. However, have a look into it and see if there's something that you can do. Because an index spool is creating a temporary index for you just to run that query. And on the whole, you never want that. Let me clear that again. There we go. Right. Your index spool is tremendously useful. It means that it can actually, run various things much more quickly than if that index wasn't there at all. It might have to actually go and redo all that work and so on that's over there. But you should be able to find a way of being able to avoid it by having the right indexes in place. Every so often, it'll be because your indexes are too wide, and it thinks that actually the quickest way of doing it is to ignore that really wide index, one with lots of columns in it and so on, and just be able to quickly create something. But still, it's worth you giving it some of your attention and going from there. Of course, the sibling of the index spool is another spool. It's the I'll move my camera a bit so that that's more in shot. There we go. The other one, of course, is the table spool. Okay. Now, it's the same kind of concept. The idea is that it pulls a whole bunch of data and populates a temporary structure in TempDB. It's just that the table spool isn't indexed. It's more like just a heap. Okay. The idea is that it's just like, okay, I just want to store a copy of this for a minute, that I'll pull back later. It doesn't need to order it and so on. Right. So I mean, the index spool is great when it needs to be able to access that in a particular order. The table spool, typically, table spool is there. It can be there for a couple of reasons that you don't want to try and persuade it not to do. And those reasons are, for example, integrity, or CTEs, like recursive, not just any CTE, but a recursive CTE. My writing's awful today. I apologize for that. Maybe my pen's a bit thick. Integrity, if you're doing an update on a table and you've got to find the rows that you want to update and then change them, quite often it wants to be able to store a copy of what it's doing before it makes the change, because if it's making the change while it's pulling data out of you understand, right? When you've got a scenario, where you've got like an update statement here, and you're saying pull the data in here and pull the data out of a particular index, right? You're pulling data out of an index and you're updating rows. It'll often put a table spool in the middle to make sure that this pulling data out of that index isn't going to get confused by these changes here, right? You got to think. If you're looking at the white pages, you have white pages in America, I'm sure. You're going through the phone book ordered by name and you're updating people's names. You don't want to find that then some name gets updated and you hit it again, right? That will be bad. You have standard locking to make sure that something else can't come along and change your name so that you might miss it. But just within a query itself, if you're saying I want to change some rows, you're pulling those rows out. You're then moving those rows while you're accessing this thing here. That's a problem. So it's nice to be able to pull that data into a table spool, be able to say, the data that I want to change is going to be this. So it can like plan all the changes and then do all the changes as the next step, right? In that scenario, table spool's good, right? You don't really want to avoid it there. Honestly, it's just fine. In CTEs, the CTE is the idea of saying we've pulled data out, recursive CTEs. We've pulled data out of something, and we have to concatenate that with data that we're getting on the recursive step. You know this. You say, get me the standard thing of an org chart. You populate the CEO, and then you say, and then join that back to itself with everybody that reports to what we've already got in the CTE. So what's happening is you're pulling the CEO in up here, and you're populating a table spool here that you're then pulling data from down here, right? So you've got a table spool going on where you're populating it here and then you're pulling it out there and looping through. As long as you're still putting rows onto the spool, you've got something that you can pull data out over here to be able to keep going with it. It's tremendously useful. In fact, another one that I should list on here is when you're dealing with and a scenario that you often see table spools in, at least, although I think there's often ways of being able to avoid having to use them, is when you've got windowing functions and you want to be able to have a query that does all kinds of things, and then you have like a count star over bracket to be able to say, and also include a column that has the total number of rows. And what you'll see is that you've got all your work going on. You've got all your work going on, getting all your rows, and then it populates the table spool. And it does a join with something which says, pull everything out of the table spool and do a stream aggregate to be able to count how many rows there are and pull that through. And that's not awful. It's just that quite often you can, depending on how much work it is and so on, it might actually be better if you can make a nice optimized way for it to be able to get that information separately somehow. But it's not tremendously awful. Where it becomes a problem is where it thinks that because it's pulled data in from somewhere, it thinks that the quickest way of being able to get that data the next time is actually to be able to store a copy of that data in TempDB so that it can go back and get it later, right? That's where a table spool becomes a problem. When it's just there for the sake of counting or joining or the integrity and so on, it's not so bad. If it's there because it thinks that it'll be quicker than going back to the same table again, the underlying table, I feel like that's where it starts to become a problem. And I'm just saying, hang on, what's going on here? Does it really need to be thinking? Does it really need to be storing a temporary copy of this data somewhere? Can't I just make sure that it's got an easy way of being able to get back at that data without having to go and store it in TempDB? Typically better indexing choices, being able to look at what's happening. I mean, at the end of the day, it's like it's creating a temporary table. It's exactly like it's creating a temporary table. It's just that you're not in control of that flow. It's doing it for you in the middle of running a query. It's what it thinks is best. And we keep reiterating that. It's what the query optimizer thinks is best. It's just that typically, I feel like it's screaming that there's a problem in some way, something that I can do better with it. Okay. Another one. Sorts. Now look, when you need to be able to say, I've got to get the data in a particular order, you're often going to get a sort operation going on. Yeah, that's what happens. Right. it doesn't mean that a sort is ever particularly good. Let's face it, when you have a sort operator, it's blocking. You've got a, I'll draw down here this time. When you've got a sort operator and it's pulling data in from somewhere, it has to see all the data before it can give you the first row out. That's blocking, makes people feel like the system's unresponsive. That application that's wants to start seeing data so that it can start dealing with it has to wait because of that sort, right? And this includes if it's a top end. So let me kind of write in here plus the top end bit, right? It might be a top end sort. Like the idea of saying, look, I've got 1,000 rows here, and I need to sort those to find the best 10 because the person said select top 10 of these. But it doesn't know if the last row that it sees from here is actually going to be the first one that it's got to give out following the sort. At least with top N, it can see it doesn't have to store all of them in order. But let's face it, if you're consuming 10,000 rows and you want to sort all of the 10,000 rows, you've got to be holding on to those 10,000. Let me quickly point something out here. So if I've got my select operator here, right, and I'm saying pull data, right, I'm saying pull data from stuff. If I've got like compute scalars or nested loop join or whatever stuff that's going on, and I'm pulling data out of a table, as soon as my select operator has got the data, I'm giving that to the application, whether that be whether that be some website or some SSIS package or data factory or whatever the situation is, some report. As soon as it starts seeing data, that application is getting it and it's able to do something with it, right? So theoretically, the query engine can then release that data for something else because it's given it to the calling application. The amount of data that it really needs to hold on to service the query might be quite small. It's just saying, give me the next row, I'll do some processing on it, and I'll give it out to the application. And it's just passing the data through like that. It's nice. When you've got a sort operator, it's got to hold on to all that data. It might only be the top N rows. Sure, it might only have to hold on to, say, 100 rows if you said top 100. But if it's a whole set, it's got to hold on to all of that. So suddenly the memory consumption is way bigger just because you've got a sort, right? And the way that you get rid of a sort is that you sort it before you run the query by making an index. Remember, an index is not just there for helping you find the data. It's about being able to have a sorted copy of the data. So if you have that index in place, when it comes to being able to say, fetch me this data in this order, it goes, got an index for that. Terrific. And it might be that a whole bunch of work that you're doing separately might actually, be a lot easier than putting a sort operator in there, right? Way too often we think about saying, oh, let's index for being able to find the data that we want. But I quite like saying, let's index according to being able to avoid the sort that I don't want, right? Because I think about the plans that are going on. Because I want to be able to make sure that my query can go into production and it can scale and all of those kinds of things. And sure, if my where clause is nice and selective and I can quickly find the 3 rows that I want, then sorting 3 rows is not really a problem, right? And I want my index to be able to help with that. But quite often, my where clause stuff will be, we'll be using inequalities like, greater than, less than, those kinds of things where they remain in that order. Like if it's equals. So for example, if you're looking for the Farleys and you're wanting us in first name order, well, If you're looking for everybody whose name is Farley, terrific, an index on that is useful. And then if you're wanting them in first name order, well, the white pages is good for that too, right? That composite index is really handy. You can find the Farleys, and then we are in first name order. If you're wanting people whose names start with Farley, so that you have the Farley Smiths and everyone else's, right? All the Farleysons and all that. When you find, you know, the ones where surname is like Farley %, we're not in first name order. We're still in last name order. It could be that, you know, Aaron with 2 A's, Aaron, is the one who's Farley - Zachariah, you know, could be at the end of the list of Farleys. You need to do that sort. If there's not many Farleys, not a problem. That might be the best one. But you know your data. You know whether you should be, you know, indexing for the sort or indexing for the where clause. But think about that. Understand the impact of it. Understand that it's going to be blocking. Understand that there is potential pain with the sort operator. Okay. Another kind of blocking thing is hash. Okay. So the hash operator, it could be a join, like a hash match, or it could be an aggregate, like a hash aggregate. But the concept is that you've got your hash aggregate, your hash operator. It's pulling data in potentially from 2, you know, if it's a join, as opposed to just an aggregate, and then it's spitting the data out according to the things that have matched, right? If it's a grouping, if it's an aggregate thing, the idea is that, well, it's been able to pull in all of the things that are, like, you know, your pack of cards that's unsorted, for example. It's figured out what things match by applying a hash function, seeing where it is in a hash table, and then being able to look at the things that landed on the same, in the same hash bucket, and figuring out if they matched. With a join, it's doing the same thing. It's just that it's creating all of the hash buckets first, and then it's pulling stuff in from the other stream of data to be able to say, you know, okay, let's apply the same hash function and see what it joins, see what it matches against from the first stream, and they might be fine, but you've got to create this hash table. And once you've created a hash table, you've then got to start pulling stuff in from the other side. There are things that it can do to be able to optimize that by keeping track of the different things, you know, the different functions that have been involved and so on. And there are bitmaps that it can create to be able to find ways of trying to do that better. But the basic concept of saying we want to populate a hash table and see what matches, it's the same no matter whether it's a hash match or a hash aggregate. And they both need to see the data, you know, all of the data before it can start producing rows. Okay, because or if you're counting the cards in an unsorted deck of cards, you don't know how many of any of them you've got until you've seen the last card, because that last card could be any suit, and you need to know that before you produce that. One difference is that if you're doing a distinct flow, like if you're just doing a distinct and it's using the hash function to be able to say, oh, I haven't seen this one before, and then it can produce that row. That's the one time when it's not too bad. However, it still has to maintain a big old hash table, and that costs, right? There's memory being used. It's got to apply the hash function and everything. Applying the hash function is really not that big a deal, but the memory that's going on is a pain. And the size of the hash table is 32 bits. That's the size of an integer that's not nullable. If you're grouping on anything that is wider than that, or if you're joining on anything that's wider than that, then you end up having a residual check to do. In other words, you apply the hash function, you just say, okay, it's landed here, but does it necessarily match everything else that's in that hash bucket? If what you're joining on or aggregating on is more than a non-nullable int, which could just be a nullable int, then it actually has to keep track of all the values that it's seen to be able to know, to be able to make sure, do that extra check, that probe residual to say, does it really match? Starts to become expensive. And how do you get rid of this stuff? Well, if you've got a hash aggregate, it's because your data is coming in not ordered. And index can help that. You can turn that hash aggregate, hopefully, into a stream aggregate, because when you're going through a pack of cards and you're counting how many are in each suit, if they're ordered, then it's fine. You can move through that. And when you're seeing heart, as soon as you see a spade, you're not going to see any hearts because you're looking at ordered data. And it can replace that hash aggregate with a stream aggregate instead. And then as soon as you've hit that spade, you can say, yes, there's 13 of those, and you can give that result out. Then it's not really blocking anymore. So a whole bunch of nice advantages to that. Right? So yeah, aggregates and matches are blocking. A distinct flow isn't, but either way, trying to maintain that that large amount of memory use is significant. There's another thing with being able to avoid a large hash, the cost of that, and that's that if you're dealing with if you're doing that because you want to see a count distinct over a large data set. Can you imagine doing a count distinct over a large data set? So bear in mind, you might have like billions of rows here, and you want to see how many different values you've got in a particular column. And so you're applying the hash functions to them all, and you're dropping them into a hash table, and you're expecting that you're going to see, potentially a few billion different values. And it's maintaining a hash table with all of those different values in, billions of them. That becomes really expensive, right? Almost guaranteed you're going to spill to disk because you're not going to be able to do all that in RAM necessarily, depending on the size of your RAM and what else is going on and so on. It's just, it becomes a pain. This is why we've got a prox count distinct, which is this concept of being able to use clever maths to come up with a pretty good guess. It's like 98% of the time it's within 2%, which is probably good enough, because when you're dealing with values that are that large, you really don't need to be accurate to the exact value. You just, you just want to know whether it's 2.3 billion or 3.8 billion. You don't need to know, all the significant values all the way down to the exact one. And if you can see a quicker way of being able to get through that data without having to resolve all of that memory, it's a good thing, right? Hash can be good. It can be the most effective way of doing something, but it can also be painful. If you've got a join going on, you might prefer to make that a nested loop so that you're able to do the work without having the expensive memory grant needed. And for that, make sure that your indexes are in place to be able to find this thing on the other side. You'll have a lot of reads, but reads on data that gets into RAM is a lot cheaper than trying to reserve that much memory and so on. And of course, the concurrency with it is way cheaper. If you've got lots of nested loops going on at once, no one's really going to care. If you've got lots of hashes going on at once, that just increases the amount of memory that your system's trying to reserve for that. Right? Of course, I just mentioned hash. I mentioned nested loops a bit, but as being a nice option on that. I also want to mention merge, right? merge in many ways is the nicest of the join methods, because you've got two sets of data and they're both ordered and you're happily walking through them. Of course, one of the clues is that they're both ordered. If you've got a merge and you've got sort operators in there, be thinking about that, right? But for merge, I really want to be thinking about the idea of the property, which is whether it's many to many or not. Right? So when you see a merge operator, there's a property in there that says that it's many to many. Let me show you what I mean. We've got two sets of data, right? I'm going to draw a line. Got a set of data over here, set of data over here. If we're doing it, if we've got data on this side, which is 1, 2, 4, 5, 6, 8, for example, and we've got data over here, which is 1, 1, 1, 4, 4, and so on, right? A merge join says, okay, I'm going to start over here, and I'm going to say, and we're going to have a pointer over here. We're going to say, right, my first value is a 1, got any ones? And it says, yeah, I have, great. And it can do the join on that and spit them out. It's non-blocking, it's nice. And then it says, okay, I'm out of ones. So it goes, okay, 2s, got any 2s? It goes, no, it doesn't have to move because this is ordered data. If there were any 2s, they'd be right there. 4s, yep, got 4s, and so on, right? It's nice. But in this scenario, this is one to many. My values are unique on this side. If this wasn't unique, if I had 2 1s, for example, in here, then I need to turn on many to many mode. And this is then how it works. It just goes, okay, I've got a 1. And it goes, oh yeah, I've got some 1s, fantastic. And it says, okay, I've got another 1. And what happens? This one over here goes, okay, hang on, I've got to go back up to here and go through this again. Because, I can't just keep going with the next one because I've got a many to many situation going on. As soon as you're in many to many mode, this side needs to be able to keep track of all the ones that were in that latest group, because it might have to see them again. And it suddenly goes into a mode where it's just like, oh, I've got I've got to do different things with memory and all that kind of stuff, and oh, it's just so much more work. How do you avoid that? Well, let's think about this. Suppose our data's actually got a 2 there, right? Suppose it's unique on this side, but we still see the many to many. That's going to be because it doesn't realize that this is unique. Right? To be able to stop using many to many mode, it has to know that one side is unique. It has to know, either using a unique index or because you've queried that one with a group by, something like that. But there are things you can do to let the system know that that's unique, right? Either within the query by doing something like a group by, or in an underlying index where you can mark something as a primary key or as a unique index, so that you can then get into that mode where it doesn't have to keep track. So it's seen those 1s, and then when it goes to the next one, it knows that it can't see another 1 because that's unique. It's really good. The other thing about merge, and let me clear that for a second. The other thing about merge, which is actually a thing for hash as well that I've kind of already mentioned. It's also a problem with seeks in general, but I feel like in many ways it's a hidden cost in merge, because people think about how merge works and they're just like, yeah, we're good with that, and they miss the fact that there is a residual. I think I've spoken about residuals to the LA user group before, many years ago. The residual is like the leftover thing. In a hash match, it's the probe residual. It says, it's that thing that says, we've applied the hash function, we know it's in this bucket, but we're not actually sure that everything in this bucket is the same value. We need to check that. That's a probe residual. But there might be more than that, right? There might be just whole other predicates going on. With merge, it might be that we see a 1 here and a 1 here. I'm sorry, I'm drawing up here. A 1 here and a 1 here, and that we see lots of other 1s as well. But maybe only some of these count as the match and the rest don't. Right? If it's saying I've got a whole bunch of potential matches, let me do a bunch more checking to see if they are or not, then potentially all of a sudden we're having to deal with a whole lot more data with the number of candidate matches. Like if you've got a table of a million rows and you're joining it with another table of a million rows, and it decides that actually they're all going to end up in the same bucket, or in the merge that they have the same join the things that it's running through the merge with, then all of a sudden a million rows here and a million rows here becomes a trillion rows that it's got to check. You know, like a million times a million. So you're talking 6 zeros and another 6. That's skipping past billions and moving to trillions. That's more money than countries that are not America have heard of. You know, that's, I mean, you know, that's nobody's that rich.
Hold on, can I call you back in about an hour?
Yeah, call back in about an hour. That's good.
Okay.
I don't know. So a residual can suddenly mean that the amount of work that's going on is suddenly way higher, right? So be careful with it. Be careful with it in merge. Be careful with it in hash, right? And both aggregates and matches, right? And also be careful with it in seeks, right? When you do a seek and you go, yep, I'm looking for the Farleys, right? You can very quickly find us. But if you're looking for the Farleys whose first names have 3 letters in them, assuming that I'm Rob and not Robert. Now that my grandmothers have both died, nobody calls me Robert anymore. But I can find the Farleys, not a problem. I can see that there's a seek going on. But then I've got this residual predicate. It's just actually referred to as predicate in plans, but it's a residual predicate. It's the leftover one. If we've done our seek, but then we've got to do some more checks to see what we're supposed to be returning. I've done whole sessions on this. Be careful about residuals. If your seek is very selective, the cost of doing a residual check is going to be small, right? If your hash is putting stuff into a lot of buckets, the cost of your probe residual might be small. If your merge is doing a nice one to many, not many to many, if it's moving through nicely, the cost of the residual might be small. But always be aware of it, because that's when some of these things that might be just fine can become problem operators. Always look out for what residuals are going on. You might not even see them in the tooltips. You might need to hit F4 and see the properties. Like, you know, seeing whether a merge is many to many, it's always there in the tooltip. But quite often it will hide the residual, won't put it in the tooltip. You've got to go to properties to see it there. And I know some really big name experts in T-SQL that have missed this before. So always get used to looking at the properties. Always. I miss this sometimes myself. It's just that when I'm trying to figure out why a query is slow, I'm looking for my problem operators, and quite often I'm needing to check what the residuals are. Okay. Interestingly, on a seek, a few versions ago, they introduced the concept of number of rows read, which was basically saying what's the seek returning before we've done our residual checks. So you can get that ratio of values to be able to see whether the residual is actually doing more work than the seek predicate. used to be, years ago, we'd turn on a trace flag 9130 to be able to separate it to the seek and then a separate filter. Sorry, this way. We'd have a seek and then we'd have a separate filter operator. I should draw it like this. We'd have a filter that was pulling the information out of a seek, and the filter would apply the residual predicate based on whatever the seek predicate was returned from the seek. It's just that, you know, that was a pain to try to do. You don't often have permissions to turn on trace flags, that kind of thing. It's just a bit annoying. Much easier to be across the underlying properties of number of rows read versus number of rows returned, and to understand the concept of residuals. So yeah, so be across that. Generally with seeks, you'll see a lookup operator. Hopefully you don't. Because of course the lookup is always a sign of a potential problem. You understand it. You see that you've got a nested loop or going on, pulling data out of a table because you've said I want data from a table. You haven't put a join in there. It's given you a join operator, that nested loop. It's pulling data out of the seek, and then it's saying do a lookup into the clustered index on the table that you're looking at. It's a lookup operator. Right? It might be fine, but at the end of the day, if your seek is returning 3 rows, it's then going and doing 3 lookups to be able to get the rest of that data. And so your 1 seek has turned into 4 seeks, 1 here and 3 there. And that's if it's got 3 rows. If you pull back 99 rows, all of a sudden you've got 100. 1 here and 99 there. And your seek isn't going to scale, because at some point it's just going to be like, you know what, I've hit a tipping point. I'm going to replace all of this with just a scan of my clustered index instead. Lookups are a pain. They're easy to fix. You just put an include. You include the columns that are being referred to down here in that lookup, which might actually not be just outputting columns. It might be applying additional checks, additional predicates to see whether the row actually should be returned up here. But you can avoid it just by saying, let's make sure that we've got the things that are referred to in the lookup, that they're in the list of included columns, they're in the index that's being referred to as being used here. Because if we can get rid of all of that, and we can just make it just a straight seek with no nested loop in there, then it doesn't matter how many rows are returned, it's not going to switch to a clustered index scan because that's always quicker. There's nowhere for it to go. It's going to be that. It's going to be quick. Lookups are just an opportunity to tune just by enhancing the index. Occasionally, you can leave them there if you're feeling like your index is getting overly wide because someone's done a select star and your lookup is actually pulling back like a ton of columns. But at some point, your lookup is just introducing the possibility of a bad plan. So be careful. I definitely include them in my list of problem operators. Okay. Last one. Oh my goodness, we must be nearly finished. Compute Scalar. Tremendously useful. Pulling data in, they do some work, they add some value, they get rid of the null for you or whatever the case may be, and it's often just fine. You've said count star, so it's worked out count big, and then it's having to convert that to an int. If you use count big, you won't see the compute scalar. But quite often they are hiding some evil in there. They might be calling like a scalar function, that's procedural, has a begin and end in it, and can't be simplified out because you're not using a late enough version of SQL. And So whenever you see a compute scalar, have a look and see what it's doing. Click on it, go to the properties, look at the defined values, see what's being called, and figure out whether it's innocuous or not. Because way too often a compute scalar is just a massive problem. It just hides cost. It'll be reporting it's really cheap, but it might be going off and calling a whole nother program in the form of a function to be able to do the work. I could easily drop in like remote query and multi-statement table value function into the same kind of bracket as compute scalar in the fact of hidden costs. You don't really know necessarily what's going on without going and digging further into other definitions of things. But do keep an eye out for these things because way too often you'll be looking at some query that's been written and some developer will have figured out that I don't mean that as a derogatory term. Well, developers are really good. Some developers trying to make sure there's consistent use of logic and so on, and so they've created a scalar function for this thing. They feel like it's all good and so on, but they pay a price because it gets called by everything. Maybe there's like a column that's been in a view, and you're saying filter on that, and it turns out that actually that column is the result of a function, and it's all of a sudden it's getting called for every row that's passing through, and potentially it's killing you. Might be fine, but it might be a problem operator. So we've listed a bunch of things. I'm just going to make my pen a little bit smaller because I want to write quite a bit on here. We have seen index spools today. We've talked about, we haven't seen, we've talked about them. We've talked about table spools, we've talked about sorts. What's next? Hash. And and that's hash aggregate and hash matches. We did a whole series almost on join techniques and so on, and we talked about merge as well. We talked about the residuals. We talked about, I'm going to come over to where my head is now, lookups. And we talked about compute scalar operators. Right? They are all good. They are all things that the query optimizer will put into into plans that it runs for you based on what you've asked for. And quite often, they're just what you need. Right? I don't want to say if they didn't need them, they wouldn't put them in, because that's really not the case. However, there's always a reason why they've put them in there. And I just want you all to be conscious that quite often these kinds of operators are the ones that I'm looking for when I'm trying to see where problems are in a query plan. At the end of the day, I'm not interested in tuning the query. I'm interested in tuning the query plan. If there's a way that I can make a query run better, I don't even have to change the query. I just want the plan to be better. Sometimes that's because because it's got a bad plan, because it's not indexed, the right index is not in place, or whatever the case may be. But these are some of the things that I look for. Anyway, let me pass back to Steve. I'll find my window, and I'll share my camera again and stop my screen share.
Rob, thank you for presenting problem operators. Thank you for attending November 2021 meeting. Thank you, and we'll see you next time. Thank you.
Thanks.
Good night.
Thanks, Rob.
Thanks, everyone. Bye.
Thanks, Rob.
Bye-bye.
Thanks. Bye.